In Chapter 7, we're going to start getting a little closer and get into this idea of inferential statistics. Again, the idea of inferential statistics is we are taking the descriptive statistics we calculate on a sample we've picked, and we use this to predict the what's happening with the whole population, predict the parameters of the population. So to get started with this, we're going to start with this idea of a sampling distribution and the sample mean. So what does that mean, and where do we get into it with it? So this first section, we're going to start off with what can go wrong. What's my sampling error? So again, most complete way to do this, to find out what's going on with a population, is to take a census, but that's often not feasible. So we use samples to collect data and make some predictions. So we're going to look at what do we mean by a sampling error and introduce the idea of the sampling distribution. So a sampling error is basically what's the error we get if we use the sample to estimate a characteristic of the population. So let's start. What's going on here? Here's a situation in 2010. Looked at the mean tax of income tax returns at $11,266. So they calculated this mean tax from a sample of 308,946 out of more than 130 million returns. Because again, you're not going to calculate it with all 130 million plus. So just to think about the situation, what's the population that we're considering? Population in this example is all of the individual tax returns in the year 2010. What's the variable under consideration? Variable under consideration is how much income tax does each person have to pay. This is a sample or a population mean. They reported the sample mean and are using that to describe the population, but that value is really a sample mean. So do you think the actual mean is exactly the same as the population mean of the sample? Yeah. No, we don't think that's exactly right. There should be there. We expect there to be error. It might. Hopefully it's close, but how close? I don't know. We know there's going to be some difference between these two, between x bar and mu. But we want to know how much error can I expect. If it's within $100, that's pretty much a good enough estimate. If it's only within $1,000, then that's wildly off. So that's kind of what we're looking at. To do this, to answer this question, we're going to look at the distribution of all of the possible samples, or the means of all the possible samples we can take. Call this the sampling distribution of the sampling mean. I know that's a mouthful. So we sometimes call this the distribution of the variable x bar, is the quickest way to talk about this. The distribution of all possible sample means of a given sample size. That's more kind of what does this, as I like, what does the mean mean, right? Okay. So this is kind of saying, yeah, what are we talking about? What do we mean by this? This is probably the easiest way to describe it. But yeah, when we talk about the sampling distribution of the sampling mean. So we're going to look at a sample and a population, and do these distributions. We're going to start with a really small population because I want to actually calculate the numbers and see this distribution. It's very unrealistically small. If this was our population, we wouldn't sample it. we would just do the population. But it kind of gets us to see what we mean by this. And we'll deal with bigger populations later. Don't you like that? We'll just deal with it later. Yeah, we'll get to it. So we're dealing with our population here is the heights of a 5-player basketball team. So that's population is a 5. Oh boy. Oh, I got to fix that. 5 starting players on the team. We're going to just call them A, B, C, D, E. The variable of an interest is their height in inches. So here is our data. We have the entire population there. We can do these calculations. But again, we're looking at some ideas of this sample distribution. So we're going to first figure out if we have a sample size of 2, what does that look like? We're going to make some observations and then find what's the probability that for a random sample of size 2, the sample error made will be 1 inch or less. Or in other words, what is the probability that if I pick 2 people off of this team and I find their average height, that I will be within 1 inch of the average height for the team. So that's what we're going to do. Now, this is nice because, again, it's a small population. I can easily find mu. I can find the population mean, which is 80 inches. But now let's look at sample size of 2. Well, we can list all of the possible samples of 2 people. AB, AC, AD, AE, BC, blah. We get 10 possibilities. We look at their heights, find the average, the mean of the heights for each of those. This would be my sample distribution. These are all my possible samples. These are all of my possible means from those possible samples. So I would be looking at this column here, this X bar would be my sampling distribution. Or my data, which we could make our sampling distribution from. Here would be our sampling distribution when my little thing goes away. I did this with a dot plot so I can visualize it a little bit easier. How spread out are the different samples we can get. These aren't the actual heights of the players. These are all of the possible results I could get by sampling at random 2 members of the team and finding the average height. That's what I mean by that sampling distribution of the sample mean. So I'm supposed to get my mean of 80. And if I look at this, there's only one of them. That's really annoying. Really one of them that has the height of 80. All of the others are different. So I'm only a 10% possibility or a 0.0 probability that I will pick 2 people and get the exact population mean. So I give myself a kind of a range. I want to be within 1 inch. If I look within 1 inch of 80, that would be 79 to 81. I see 3 out of the 10 samples will give me that. So the probability is 0.3 that my sampling error will be 1 inch or less by picking 2 of the players at random. Still not great, huh? So we're going to do this again with a different sample size. We're going to look at a sample size of 4. We pick a sample size of 4, there's only 5 possibilities. If I look at those means from those 5 possible samples, I get this following chart and this following dot plot. And again, if I'm looking at within 1 inch of the actual mean, none of those samples has the mean value of 80, which is what the population is. But 4 of those 5 samples are within 1 inch of 80. So we would have a probability of 0.8 that the mean value is within we're within 1 inch of the actual mean value. So carrying this on a little farther, and again, with a small set we can do this. With a large set, we couldn't do that. If we look at differing sampling sizes, here's with the sample size, we just pick one person. That's basically my data. Sample size of 2 we looked at. We looked at 4, here's 3, and 5 has picked everyone. That's the population. And you notice as when you look at this and we compare those, as my sample size gets bigger, my population, my sample means cluster closer to the actual population mean. And that's one of the things, and it kind of makes sense. The more people you pick out of that sample, the better chance you will get a group that is going to be pretty close to what you want. So this table here, we're looking at, again, with all the possible sample sizes, how many possible samples we can get, and how many are within 1 inch of mu. We'll see actually, just by picking one person, we got a better shape than picking 2. Interesting. But then after that, 50, 80%, 100%. If we're looking within half of an inch, 0, 20, 20, 60, I'm still not doing too bad with 4 out of the 5. But again, as the sample size gets bigger, the sample means cluster closer around the population mean. So the larger the sample size, the smaller the sampling error, which is kind of, makes sense. It's pretty intuitive. So that's just this first section, the introduction to this idea of the sampling mean and the sampling error. So go ahead and try these problems.